Okay, so today we are working on an application section 6.4, and it's called work. So first of all, what is work? This concept. Well, work is performed by applying a force. Now, a force is like you're pushing something across a table. So imagine you place a brick on a table and you push it by applying a force. Well, when you apply that force, you're obviously going to move that brick a certain distance. So what work is, it's performed by applying a force to an object and moving it a distance d. Okay, so work is equal force times distance. And for this introductory calculus class, this is actually a physics application, and force and what we call displacement are actually vector quantities. So this is actually a dot product, but we kind of ignore that dot product and just say it's force times distance, because if we just, if we had a surface here and we had a brick right here, right? Oops, let me fix this brick just so we understand this. You have a brick here and you apply a force in this direction. This is your force. Obviously, this brick, when you apply the force, you're going to slide this way. So the force is in the same direction as the motion of the object. Okay, so that's why we simply call it, when that's the case, it's really just force times distance. And that's as far as we're going to go with that. If you're taking a physics course, you'll deal more with this later here. Okay, so I just wanted to mention that there. Now, this is an amount of energy. Okay, so work is an amount of energy and it's measured in joules. So we do have to discuss a little bit about units and what is a joule, but it's an amount of energy. I mean, you might have taken a physics class or maybe a chemistry class where you talked about kinetic energy and potential energy. Those are units of joules. Okay, so work, we simply abbreviate it with W for work and force times distance. Okay, well, what is force? This is actually Newton's second law. Note, force is actually mass times acceleration. Now, we'll be dealing with a metric system, which is standard international units, as well as something called customary units, or what we use in the American system here. Okay, but mass is a unit of kilograms. Acceleration is the rate of change of velocity. So acceleration is actually, in the metric system, meters per second, which is velocity per second. But what we normally say, and when we have meters per second, which is the units of velocity over second, right? This becomes the rate of change of velocity per unit time, but we don't usually say meters per second. We shortcut it and say meters per second squared for acceleration. Okay, so that's just something I wanted to note there. Now, when you multiply a kilogram times a meters per second squared, that gives you the unit of force. And we shortcut, or we make a little precise notation of what is kilograms times meters per second squared. We call that a Newton. So a Newton, obviously named after Sir Isaac Newton, a Newton is a unit of force, usually abbreviated with the letter N. Okay, so force is mass times acceleration. In the metric system, it's kilograms times meters per second squared, which we give a new name called a Newton. Now, what about mass in customary units? Well, mass in our units is actually sometimes abbreviated as pounds mass, but it's actually called a slug. You don't have to worry about this. You're not gonna have to worry about a slug, but slugs actually are units of mass. It's the equivalents of kilograms, okay? But sometimes you'll see pounds mass. And then acceleration in customary units is feet per second, so that's feet per second squared. And so force is pounds mass times feet per second squared, which we usually say as pounds force, okay, in the American unit. So when we get to our problems, this is not going to cause any issues here, but you'll see when we get to there. Pounds force is units of force, okay? Now we've defined force as either a Newton or pounds force. Now remember, what was work? Work was force times distance. So in the metric system, our units of force here is called a Newton. And our units of distance is called a meter. So work is a Newton times a meter, a force times distance. And then we give that a new name after Mr. Joule. That's what a joule is, a unit of energy. And remember, work is an amount of energy, okay? So when we do our calculations for work, we're gonna end up with joules. So these are the units for work. Now, in customary units, we would use pounds force times a foot, which is called foot pounds, okay? So right here are the two units of work that we're gonna be dealing with in our problems today in this section when we calculate work. So in the metric system, work will be defined as joules, and in the other units, American customary units, foot pounds, okay? And both these are units of energy, okay? Now, I mean, I'd give you acceleration if you don't know it. You don't have to memorize those, don't worry about that. But I do want to make a note, acceleration of a falling object is due to gravity, g, where gravity is 9.8 meters per second, or 9.8 meters per second squared in the metric system, and 32 feet per second, or 32 feet per second squared in customary units here, okay? This, you don't have to worry about, if you forget these, don't worry, they'll be given to you on an exam if you need them, okay? All right, so where is the application part of calculating work? Well, the problem is work is force times distance. I mean, it's a simple calculation. It's just that the issue becomes, what if force is changing? Okay, what if you have a changing force? That's what we're going to look at. So what we're going to first begin with is spring force. Okay, and you might have covered this in algebra, but now we're going to go back and look at it, and we're going to use calculus to calculate the amount of work done by a spring. So what I've drawn here is a surface, and here's a block. It's attached to a spring, and this is stationary here. So a spring has a natural position, an unstretched length, right? And this length here represents, from here to here, represents the spring unstretched length. But obviously, if the block is here and you take this edge here and you attach it to the block, you've now stretched the spring. And probably as a kid, or you've probably taken a spring and you stretched it, like a slinky. Well, in order to stretch the spring, you must apply a force, right, to stretch it. So when we apply a force to the spring from its unstretched position, the spring force changes, and it is directly proportional to the distance stretched from its natural position. So what they're saying is, you take a spring in natural position, if you pull it, you have to apply a force to get the spring to attach it to this block. So you applied a force to get it here, and that force is directly proportional, or varies directly with the amount the spring is stretched. So if this is the string's natural position, you stretched it this amount to hook it to here. Okay. So this might be familiar to you. The spring force function, f of x, is equal to kx. You might remember that as Hooke's law from algebra. So what this says is, the force is a function of x. meaning that if you stretch a spring 2 meters, right, then the force varies directly by this constant K. And what is K? K represents the spring force constant. So see, if you had a spring that was, say, F of X was equal to 4X, that would mean that, and this is in meters and this is in newtons. If you stretch the spring 1 meter, your force would be 4 newtons. If you stretch the spring 2 meters, your force would be 8 newtons. If you stretch the spring 3 meters, your force would be 12 meters, and so on. So this is an example of a spring who has a spring's force constant, K, equal to 4. That's just an example there. All right. So now, remember, K is the, right here, oops, K is the spring force constant. X represents the distance stretched from its natural position. We got to remember that. Okay. All right. So let's do an example, and hopefully, if it's, we can flesh out any questions that you might have. So here's an example. A spring exerts a force of 100 newtons when it is stretched 0.2 meters beyond its natural position. So if we look at this picture here, here's the spring at its natural position. And notice I'm going to mark X. I'll put X over here. This will be my X axis. I'm marking X here as 0 when it's at its natural position. Now, this first sentence here that I've highlighted says, when you stretch the spring from its natural position to 0.2 meters, what force is required to hold the spring there? It's 100 newtons. Obviously, to stretch the spring from 0.02 to over here to 0.8, your force is going to increase, right? Because the further you pull on the spring from its natural position, the larger force you're going to apply. So what this question is asking here, it gave us some information that we will use to find the spring's force constant. And the question here is, how much work is required to stretch the spring 0.8 meters from its natural position? So they want to know what's the amount of work to stretch a spring from 0 to 0.8 meters. Okay. So the first thing we're going to do is use this given information up here to find the spring force constant. So with any of these spring problems, that's the first thing you're going to do. And you might have done this in algebra if you remember here. Okay, so the first thing here is step 1 to find K. Well, we know what's a relationship between force and distance stretch. It's F equals KX. Okay. Now, using our given information here, we were told when X is 0.2 meters, right? When X is 0.2 meters, the force is 100 newtons. So we can say, all right, our force here, we're going to make it 100 newtons. And now we have our spring force constant times, and then what's our X value here? For this one, our X value was 0.2 meters. Okay, now we can solve for K. So from there, we can see K is equal to, well, if you take 100 and divide by 0.2, what happens there is you get 500. So we get 500 newtons per meter. So this right here is our spring force constant. Okay, so now with that, we found K, the spring force constant. Now what we're doing in our next step is we're going to define what's our force function. Well, we just plug in K. So our force function here is F of X is equal to 500 x, right? That's your force function there, okay? Because we know, remember, F equals kx, and we found k to be 500. And these newtons here would actually be joules in this case, okay? So let me get rid of that there. Oops. Okay, that's the joules at the end to make sure we put the units in. All right. Okay, so now what I'm going to do is graph f of x. So it's like graphing f of x equals 500x. So this is the equation of a line, right? So over here, on the right here, I draw a line like this, right? That slope is 500. So let's label this graph as f of x is 500x. Now let's take a look at this graph here, because this is going to be important when you take calculus to your science classes. You use calculus. So if you have a function here, f of x equals 500x, and this is f of x versus x, meaning the vertical axis is force, which is in units of newtons. The horizontal axis is in units of meters. So if you look at this area here, if you took an arbitrary cross section here, right here, like say like this, say I take a chunk like this here, okay? My question to you are, what are the units of area for this thing? Well, remember, this partition has a height, correct? What would the units of the height be? I mean, what's this distance? What's the units of this? It's what?
Newtons.
Newtons. Now, what's the units of the base or width?
Meters.
It's meters. So how do you find the area of a rectangle? Remember, it's just what? Base times height. So what would the units of this thing be?
Joules, right?
Yeah, because it would be newtons times what?
Meters.
Meters, right? Because of the height is in units of newtons. The width here is in units of meters. So obviously the area has units, Newton meters, which we know is a joule. So what that should be telling you then, when you look at the area below a curve, what are the units of area? It's Newton meters, which is a joule. So what you're going to take from this class to your science classes, if you graph newtons versus meters and you find the area below this function, this area represents the amount of energy, which is joules. That's where the integral comes from, because we know how to find area below a curve, right? We set up an integral. And so this is the application. So to find the amount of energy or the amount of work, right, to stretch the spring, we find the area below the forcing function, which is in units of joules. That's where it comes from. Okay, so now, so step one, we found our spring force constant for this spring. Here's our function, we graph it. Now you don't really have to graph it, but I'm just making sure we understand visually what we're doing here. So as I mentioned here, we can get the answer geometrically if you understand what integrals are actually doing and the application of it in this problem. So let's make a little note here. See, here I have drawn the area under the curve from 0 to 0.8, correct? And if you look at this entire area here, we can find this area of a triangle, correct? The area of a triangle, I want to just mention this, area of a triangle is 1/2 base times height, right? So this triangle has a base of what? What's the base here? it's 0.8, correct? And that's in meters, right? So let me put the meters in there. 0.8 meters is the base, and the height of that triangle is 400 newtons. How do I find that height? Because this function is 500x, right? So what's 8/10? 8/10 of 500. 0.8, when x is 0.8, f will be 0.8 of 500 is 400. That's how I knew that point was 400. 0.2, right? 0.2, 2/10 of 500 is 100. See, this was the given information. Remember, when you stretch the string 2/10, the force was 100 newtons. So here we know our function. We can find this entire area. This base is 0.8. The height is 400. So what do we get for this area here? It's 0.4 of 400. That's 160 joules. And see, what's important about this is this area here represents the amount of work required to stretch the spring from 0 to 0.8 with this force function, because the force changes. That's your answer done geometrically. Okay. But suppose we want to calculate this with an integral. What do we want to find this area with an integral? We should get that, correct? So pretend that we just have a function 500x, and we'll do the step 3. Find the amount of work required to stretch the spring from 0.2 meters. I'm sorry, 0.2 meters to 0.8 meters. Oh, this is the area from 0 to 0.8, correct? But now we want 0.2 to 0.8. So in the problem, I have to put how much work is required to stretch the spring 0.8 from it. Oh, that's probably a mistake there. Then in my notes, it looks like it is. Okay, so that's fine. So here, be sure you fix this. So this question said, I got to fix this. Sorry about that. This right here, that shouldn't be 0.2. So in this problem, let's go back to the problem. It said, how much work is required to stretch the spring 0.8 meters from its natural position, from 0 to 0.8. So we want this entire area here. So step 3 is to find the amount of work required to stretch the spring from 0 meters. Okay, from 0 meters to 0.8 meters. Okay, I noticed in my notes it had 0.2. I think that was an older version of my notes, but that's fine. Okay, so now let's go ahead and work on this. So our work then, your work would be, in this case, the integral from 0 to 0.8, okay, of your forcing function f of x dx. So see this integral here, right here, if this is your forcing function f of x, which we had written before, this is f of x, right? And you want to find the area below this curve from 0 to 0.8, this is the integral. We did it geometrically with a triangle. Okay, so now what we're going to do is say, okay, let's finish this off. So work then is equal to the integral from 0 to 0.8. Our forcing function was 500x, and then there's your dx. So here's what we need to work out here. So obviously, we can take the 500 in front, but what's the integral of 500x? That would be 250 x squared. And this is evaluated from 0 to 0.8. And so now we got to plug in 0.8 there and plug in the 0. So what we end up with is 250. And when we plug in 0.8, we get 0.64. Subtract, and you plug in 0, you get 0. And if you get your calculator out and you calculate 250 times 0.64, you end up with 160 joules, which is the exact same answer we got when we geometrically found this area using the triangle there. Okay. So there we go. So that was our first work problem with the spring. Okay, any questions on this?
So we couldn't have, I mean, looking at like the work equals force times
Distance? Right.
Yeah. So we wouldn't be able to find that with that basic equation.
Right, and that's the question, and that's the thing to key on. Why can't we do that? See, the reason we can't is because your force is not what? The force is not constant.
Okay.
See, because, see, if we, let me see if I draw a picture here. So, see, suppose we just took, watch, I'm going to draw a graph here. We're going to take suppose we take that brick and you're just going to slide a brick from 0 to 2 meters, okay? We're going to apply 0 to 2 meters. But what we're going to do, say our forcing function, our force, we're going to apply, say, 10 newtons of force. So if your force is constant, then the forcing function would just be a horizontal line, wouldn't it? Right? This is f of x equal a constant, 10 newtons, right? That's just, you're going to push a brick with 10 newtons and you're going to move it 2 meters. And if you think about the area under this curve, see, what's this area equal to in this case if the force is constant?
Be 20.
Yeah, because it would be the force times the what? Distance. Right? See, that's the case where you just multiply the force times the distance. But why could we not do that in this case? It's because your force is what? It's not constant. It's what? It changes.
It's changing.
With
It's
distance.
increasing.
Right.
Gotcha.
That's why we have to use the integral. Okay.
And that's where the spring constant comes in.
Yes.
Because that's what's changing it.
Right. It's
okay.
like,
Perfect.
yeah, the more you stretch it, the greater the force.
Gotcha.
And that's the direct variation. Okay. All right. So let's get rid of this here. All right. So now that we've done that, we're going to look at another application. Okay. Now this one here, we have a chain is being wound up around a pulley. So here's our chain and here's our pulley, and the chain, this thing is going to rotate and the chain is obviously going to wind up around the pulley. Now, if the chain is 100 feet long and weighs 15 pounds per foot, how much work is required to wind the entire chain around the pulley? So I want you to think about this. See, if you had like a handle on here and the chain was 100 feet long, you'd have to put a lot of force to get that thing to rotate initially, right? But once the chain gets wrapped around, like half the chain is around the pulley, then you're going to apply less force, right? So because there's less chain hanging as you wind it up. So again, you have a changing force here, okay? Because the more that it gets wound up to the top, right, the less force you have to apply to rotate this thing, okay? So again, let's talk about our note here. Write this note. Note. Force is equivalent to weight. Now that's another thing. When you step on a scale and it says you weigh, say, 110 pounds, that's your weight. That's not your mass. We all know that if you go to the moon someday, you're going to weigh less on the moon, right? That's because gravity is less, but your mass doesn't change, right? Your mass on Earth is the same as your mass on the moon, but your weight is actually changing because of gravity. So weight is a force, okay? So force is equivalent to weight. Now, what is the weight, okay, of this chain? Because the weight of the chain would be the density of the chain times its length. Okay, so if we were going to say, okay, this weight of this chain is, I don't know, 1,000 pounds, okay, then the chain would have a certain density, okay, and the density would be pounds per foot. And if you multiply by feet, which is its length, you'd get the total weight. So if you know the density of the chain in pounds per foot, and you have a certain length of change, and you multiply density times length, you will get the weight, which is the force. Okay, that's a little tricky here. Okay, it's like if you're trying to, if you buy a chain, if you're holding up a chain in the air, and that chain has a density of 1 pound per inch, right? 1 pound per inch. It's a really thick chain. And you buy 12 inches of that chain, and it's 1 pound per inch, that chain will obviously weigh 12 pounds when you buy 1 foot of it or 12 inches of it. Okay, so here we look at our chain here, and we're going to say, all right, here's our pulley. We have 100-foot length of chain here. What we're going to do is draw a y-axis this way up to here, and we're going to label the top most part as 100. And if this chain is 100 feet long, the bottom is 0. Okay. So what we do here in this type of problem is we want to say, okay, we know that to move a section of the chain from the bottom to the top is going to require more work than moving a section of the chain from here, the middle, up to the top. Why is that? It's because the distance to move this chain to the top is greater than the distance to move it from here up to here. And remember, work is force times distance. So what we do is we say, okay, let's take a little section of this chain. Okay, we take a little section of the chain, and what we're saying here, what's the little length of this chain? Well, we're going to partition the y-axis. So what we're going to say here is, if we look at this little section of chain, which I've drawn right here, its length will be delta y. And that's because this is our y-axis. So we take a little section of this chain, and we call it delta y. All right, so let's write that down, this little note here. Note, delta y represents a small length of chain, which is a small length of chain. Okay. Now, if we defined this to be an arbitrary section of the chain, and we know work is force times distance, how far does this little section have to move to get to the top? So in other words, we're saying, what is this distance here? So I'm going to draw a little thing here like this and say, what's the distance from the top down to here? Our distance d.
100 minus delta y.
Yeah, so remember, delta y, though, is the little arbitrary length of the chain. But where is this arbitrary piece located? Remember when we had an x-axis? So let me just remind you, when we had an x-axis like this, right? And a y-axis, and we drew an arbitrary partition here, like this, what was the location of that arbitrary partition? Remember, we said it was just what? We made it an arbitrary what? X value, correct? It's just some X value. But now we're not partitioning the X axis, right? We're partitioning the what? The Y axis. So where is that section located? At an arbitrary value of Y. Okay, so you're just saying, hey, this is at some value Y. It makes sense because if Y was 50, what would the distance be? 50. How'd you calculate that? 100 minus 50. If this Y value was 40, that distance would be 60. How'd you calculate that? 100 minus 40. So we're calling this little section of chain at an arbitrary value of Y. That's what's written right there. That's an arbitrary value of Y. Therefore, that distance is simply equal to 100 minus Y. Okay. So it's a kind of a little, it's so easy, it's confusing. You're saying, okay, I have a length of chain, it's 100, so I draw a Y axis, I take a little section located at some arbitrary Y value, its thickness is delta Y. It actually represents a small length of chain. Okay, so we have our small length of chain here, and we know we have to move this arbitrary length this distance. Well, on this frame of reference, our distance is 100 minus the location of that delta Y, which is Y. So there's your distance there. Okay. So it's like we're doing just an arbitrary crossing. It's like when we found volumes of shells, we found an arbitrary shell. So what we're doing here is we're finding the work on that arbitrary partition here. That's what actually we're doing here. Well, the work is equal to force times distance, right? We know that. Now, here, we have to write this out. In this particular problem, in this case, the weight or force, oops, what was that? Of our partition of chain is F, which is our weight, is now we have to go back to what I wrote up here. What's the weight or force of that chain? It's the density of that chain times the length. Now remember, if we go back to the original problem, they gave you what? Right here, 15 pounds per foot. This is actually a density. Okay, so maybe I'll make note of that. It's a density. It's 15 pounds per foot. So down here, what we're going to say, okay, our force then, or the weight of that partition is the density, which is 15 pounds per foot, times the length of that chain. And what's the length of that chain? It's delta Y. That's the length of the chain, which is in feet. Because remember, this is a length here. It's an arbitrary length. It's an infinitesimally small length of chain, but its units have to be in feet. And the density of chain is 15 pounds per foot. So what this does now, it gives us our forcing function. So our forcing function for this particular chain is simply 15 times delta Y, right? That's just the density times the length, and those will be in units of pounds. So this is the actual forcing function for this. That's the force of an arbitrary piece of chain. It makes sense here because, see, if this chain weighs 15 pounds per foot, if you take 2 feet of this chain, right? If your delta y was 2 feet, the chain will weigh 30 pounds. That would be the force. If your change of y was 4 feet, right, then the weight of the chain, which is the fourth, would be 60 pounds, okay? So this right here is the actual forcing function here, okay? I mean, it's so easy, it's confusing. It takes a little bit of thought to see this. Okay, any questions on that part there? The chain is always a tough one when you first see it. Okay, so what we have now is we had to do all this conceptual work just to get our force. But remember, we're trying to calculate work. So we now have a forcing function. But work is force times distance, right? So what about the distance? Well, that's what we did earlier, right? We said, okay, if we look at our picture here, we see that the distance, right? The distance that our arbitrary partition has to travel to get to the top is 100 minus y, okay? So now we have our distance then, d is equal to 100 minus the location of that arbitrary partition, which is 100 minus y. All right. So with all our work problems, it's always force times distance. And these are the ones you have to find. It's always force times distance. So now we can finally get work. So finally, okay, work. Okay, and I'm just make sure we understand that's not the weight, that's the work. The work is equal to the integral. Now, let's go back to our little picture here. Remember, this is an arbitrary partition. Now, this is like an arbitrary value of y. These partitions, like you could have one down here, all the way up at different values of y. So where are we summing up these partitions? We're summing up these partitions from the bottom all the way up to the top. So it's like we're taking a partition. We take a slice here, we take a slice here, we take a slice here. We take this slice all the way until we get to the top. So we have to sum up these slices from where? From 0 all the way up to 100. So in our integral, we're integrating from 0 to 100. That's where we're summing up our little arbitrary delta y's. Now, what's our forcing function? It's 15 delta y, but when you put it into the integral, right, remember, you're letting delta y go to 0, so it becomes dy. So see, this part here is your force, and then what's the distance? It's 100 minus y. Okay, and that right there is the integral that will give you the amount of work to roll up all of this 100 length chain around the pulley. Okay, that's what's tricky there with that one there. All right, so now once we got that, we just integrate. Okay, so let's go ahead and do this. So the 15 is a constant, right? That's always a harder part. And then we have the 15 as a constant, so then we have to integrate 100 minus y. Well, the integral of 100 is obviously 100y, and then the integral of y is y squared over 2, and this is evaluated from 0 to 100. 0 to 100 there. So when we plug this in, we get 15. When you plug in 100 times 100, that's obviously 10,000. Minus, well, 100 squared is 100 times 100, that's 10,000 over 2, and then we subtract 0. And so here what we have is 15, and then we have, this is 10,000, subtract 5,000. So that's obviously 15 times 5,000, okay? And 15 times 5,000, if we get our calculator out, it would be 75,000. Now, what's our units here, though? If we go back to our units, see, our force was in pounds, and I forgot to write my distance. That's in feet, right? Our distance is in feet. Okay, so let me clean that up a little bit. That was our distance in feet. And so our final units of work will be what we call foot pounds. You may have heard that before. So this is foot pounds. And right here is our final answer here for the amount of work to wind up all that chain. Okay. Now, springs and chains, yeah, those always are a bit challenging when you first see them, but you do have to, give it some thought there and think through, right, why the force changes here. Because to move this section of chain, which is down here, which weighs exactly the same as that, to move this, you got to move this one at the bottom 100 feet. This one's at about 90, right? So you got to move it it's at a height of 10. You got to move it 90 feet to get to the top. This one's at 50, you got to move it 50 feet to the top. So each section of chain requires a different amount of work. That's why we have to integrate it, okay, to get that one there. Okay, let's stop there. Okay, any questions on that one? Because I know that's a tough one. At this point, you might not even know what kind of question to ask yet, but that's a tricky one. Any questions on this one here? Okay, well, we'll go ahead and move on here then. Because we did a spring, we did a chain, and now next what we need to do is get to tanks that are full of water, a fluid, okay? So now we got this picture here. We're gonna get started on this and then we'll take a break then. All right. Now in this problem, this is our example here, example 3. And what we have here is a vat. It's just a tank that's shaped like this, triangular. It comes to a point at the bottom here. Okay, I'll give you time to draw this, but I kind of pre-drew it to save a bunch of time here. So the vat below is completely full of a fluid of density 1,000 kilograms per cubic meter. Now here's the thing. This right here, kilograms, is mass, right? But as I mentioned earlier, that force is actually mass times acceleration. Acceleration due to gravity was 9.8 meters per second squared. So in this problem, this is a density, but it's a mass density. If you multiply by acceleration due to gravity, then you get what we call a weight density or force density. Now, in your homework, some of them, when they give you a mass density, you have to multiply by gravity to get the weight density. On the exam or any problem I give you, exams are final, you'll always be given a weight density. You will never have to worry about multiplying by gravity. But that's the case in some of the homework problems if you actually look at the text and the examples they do, okay? So anyway, this fluid here that's completely full in this tank has a weight density of 9,800 newtons per cubic meter. Now here's the question. How much work is required to completely empty the vat? And again, this is basically saying how much energy is required to pump all the water out of this vat. Now notice the water level only exists from here down to the bottom, but the outlet is 2 meters above the top of the tank. So if somebody was designing this, they'd have to know what kind of pump do I need that can handle that amount of energy to pump this vat completely full. Like, and if you wanted a certain amount of time, then you have to look at how much power you need in that pump. So that's kind of what we're looking at here. So you're given this vat here, and you're given its dimensions. So from the bottom to the top is 3 meters. The outlet where this fluid is going to be pumped up out of the vat is 2 meters above the top. Okay. The length of the vat is 8 meters. Okay. And the length across the vat on the top is given over here. That's 3 meters. All right. So with that said, here's what we're going to do. If you take a slice of this tank, right? If you just sliced it at one place, you take an arbitrary slice, you get a rectangular solid here, right? If you just sliced it, it would be rectangular. Okay. So if you have a rectangular solid, which represents a slice of this fluid, the volume of that rectangular solid would basically be its length, right, times its width, times its height. Okay. So the volume of the slice, okay, we know the length of the slice would be 8 meters, right? Because that's the length of the tank. But what about the width and the height? That's what we're going to do. And this is where our mathematical modeling has to come into play. So I need to model this tank with a function. So what we're going to do here is I'm going to say, okay, let's pretend our X and Y axis, our Y axis goes right here in the middle. So I'm going to kind of draw this right here. So this is my Y axis that I'm going to use to model this tank. Watch. There we go. Give me a straight line there. There we go. And here's my X axis over here. Okay. So this is X and this is Y up here. Oh, I've already drawn that, Y. Now, what I'm going to do is draw a function here, use a red color here, that goes like this on this coordinate system. Okay, so let me get this in place here. Oh, come on. There we go. So what I've drawn is a curve right here, this line here. Okay. So this line here, right here, goes right on the edge of this tank. Okay. So when you look at this picture here, I'm going to kind of draw it down here. Let me grab it, move it over here. So what I'm doing here is I created this, oops. Well, that's interesting. I guess yeah. We'll just move it out of here. So you can see there's my function there, right? So this right here is my function on a Y and X axis. So let's go back to that, okay? There's my function. All right, so let's get that out of the way now. So notice I've drawn a Y axis here and an X axis here, and I'm going to look at these 2 points and draw a function. So let's go down to here. So here's my X axis, here's my Y axis, and here's that line that I drew through there. It goes right through here. Okay. Now, if we look at the tank here, that's way up here on top. Let's see if I can scrunch it down a little bit. It might be better if I go this way. It gets a little smaller, huh? That's a little better here. Okay. So the thing is, what I need to do is, if I let this be the function that goes to this edge here, I draw a little partition right here, okay? Right here. That's this arbitrary partition you see up here. Okay, these two are there. I'm gonna go back the other way, make it a little bigger. Sorry about that. See if we get that in there. All right. So with that, if we remember, the tank only has fluid from the bottom all the way up to the top. So notice I've highlighted the region where the water is in the tank. It only goes from the bottom to here. And the outlet of the tank is 2 meters above the top, right? So notice here, I've marked it as 5. Now, the thing becomes, okay, what is the equation of this line here. Okay, so let's do this. We have to look at our points here. So going back to the tank, let's look at this right here. What's the length all the way across the tank? I had mentioned it's 3 meters, correct? So if this is 3 meters from all the way across, what's the length halfway across the tank? It would have to be half of it. So the length right here, from here over to here, would have to be 3/2 meters, right? So when we go back to our function down here, this ordered pair here would have an x value of 3/2, but a y value of 3. Okay, that's based on the dimensions of this tank. This ordered pair down here is obviously 0, 0. All right. So what you're seeing here is if I draw this triangle here, let's see if I can do it with this. If I take this rectangle like this across here and go back to here and come back to here, oops, right there. Okay. And I take this rectangle that I drew, see that rectangle fits right here, right? Just like that. That's what we're saying. There's a little bit bigger here. But what we're seeing is I'm trying to model this cross section, right? This cross section here that represents a slice of water, I'm trying to model it with this function down here. Okay, that's what we're doing here. So I have a function. Now I have an ordered pair here, right here. So now I know what's the slope of, this is a linear function, right? So this function then would have an equation y equals mx plus b, but b is 0. What's the slope of this line? If this is 0, 0, I can see my change of y is 3, and my change of x would be 3/2. So the equation of this line would be y equals change of y over change of x. My change of y is 3, my change of x is 3/2, right? And that would be x. Now, if we simplify this, right, 3 divided by 1.5, it becomes y equals 2x. So see, this is the equation of this line right here. So now I have the equation of the line, and I draw this arbitrary partition right here. Okay. If I draw a partition here, this is at an arbitrary value of, this point here is an arbitrary x comma y, where x represents the distance from the y-axis to here, right? And y is the distance from the x-axis up to here. What's the thickness of this partition? It's delta y, okay? Delta y. Now, I'll try to do this again here. So if we go back to this partition here, I'm going to draw it again, except I'm going to draw a little bit bigger here. Here, coming up to here, coming across back here. Oh, that's not going to work, is it? One more time. Here, 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 and here. Here's my arbitrary partition here, and then I'm going to bring it down, and we're going to put it right here, like this. So you can see, I just want you to understand that that x value that I've drawn here only reaches halfway across this thing. So if I cut this in the middle, right, that's x. That means over here, by symmetry, this also must be x. So when I take this partition and put it right here, right, you can see it's x and x. Now this partition also has a little tiny height here, like this, right? Just like this, right? Now what's this little tiny height equal to? Well, if I go back to my model, that little height is delta y. So see, this partition here that I've drawn has a thickness of delta y. Now the question becomes, okay, well, what's the length of this partition? Well, that's where I go back to the tank. What was the length of that tank? It was 8 meters. Okay, what that means then, oops, let me go back to that. I don't want to grab that. If I come back to here, the length of this tank then is 8 meters. So when we look at what's the volume of this actual slice, well, its length is 8 meters. What's its width? Its width is not, it's an arbitrary width. It's what? X plus X is 2X. And then what's the height? That's delta Y, to finish that off here. Okay, so I'll leave that slice for now right there so we can look at it. And let's try to get to a point where we can take a break. Okay, so we need to know the volume of this arbitrary slice. Remember, this is an arbitrary slice of that tank. Well, we know that the volume of this thing up here, which I wrote up there, the volume is equal to the length times the width times the height. So the volume of the slice, okay, we knew its length was 8 meters, just looking at it. That's its length, okay? Now, what's its width? Its width is 2x. It's this distance. Remember, this is all based on this arbitrary partition, which is in the tank. And then what's the height of this partition? It's delta y. So we put delta y. And these units would be meters cubed because they're all units in meters. And so if we simplify this, the volume of our slice then, if we multiply 8 times 2, oh, so that was 8 meters. Oh, I shouldn't have put that there, huh? I'm sorry. Let's get this out of here and put the 8 there. Okay, so the volume of the slice then is 16x delta y, and this would be in cubic meters. Okay, but now, just as before, if we have delta y, we have to express x in terms of y. So this is our relationship between x and y. If y equals 2x, then we can see x will be y over 2. Okay, so we're going to replace x with y over 2. So what we now have is 16 times y over 2. Oops. We have 16 times y over 2 delta y cubic meters for the volume of our one arbitrary slice. And finally, we simplify this down, so we get the volume of one arbitrary slice is equal to 8y delta y cubic meters. Okay, so there we go. I know it's a bit of work to get to that point. We went through this in as much detail as I can. Okay, so this right here is the volume of this arbitrary slice. And that arbitrary slice is right here in this tank. That's what it is there, okay? And that is a little, there we go. So that's right there. That's what we're doing. We're modeling it with this function here, okay? Now let's get rid of that now. All right.
I'm sorry, Professor, where did you get the y minus 2?
Oh, okay, hold on a second. Did I write y minus
for-
2? You mean the y over 2?
Yeah.
Right here. See, if y equals 2x,
Oh, got it.
right, we solve for x, which is y over 2. Okay, maybe I should write that down, so I'll put that up in notes. So here, this implies that x equals y over 2. I'll keep that in there, okay? All right, we got a little bit more here. And I know this is a tough section, it always is. Okay, so now we got that. Now remember, what is work? Work is force times distance. So we need to find, go back to here. We need to find the amount of work to remove this volume of fluid out this outlet. But if we know volume, right, and we know the density, then we can get the weight of this arbitrary slice. And remember, weight is force. So the whole idea here is we're given a tank, we take a slice, we got to find the weight of this slice. That's your force. And then we have to say, okay, how far do we have to move this arbitrary slice out the outlet? That's our distance. So the weight of the slice times the distance we move it is your work. That's what we're trying to do here. So we've broken it down where we said, okay, we modeled our slice with this function. Now we got the volume of the slice. Everything is in terms of y. But now we have to go here and say, okay, what's our force? Our force is the weight of the slice. But the weight of the slice has to be the volume of the slice times the density of the slice. Okay. Now, what is the volume of our slice? That's what we got. That was 8y delta y. And this was in cubic meters. Times, okay, what was our density of our slice? That was given as 9,800 newtons per cubic meter. Okay. Finally, we get to this. What's the weight or force of our slice? It is, well, obviously 9,800 times 8y delta y, and this is in newtons. So this right here is the weight of that one arbitrary slice, which is actually our force. All that work just to get to this, okay? So now we have our force. This is like your forcing function. Okay, and we can finish this off and then we're gonna take a break here. All right. So now we have our force, which is the weight of our slice, which was calculated by the volume of the slice times the density. Now we need our distance. So we go back, how far do we move this arbitrary slice out the outlet? Well, let's go back to our mathematical model here. Here's the location of the slice, and we got to move this slice up to 5, right? And so your distance then is defined to be from this top down to that arbitrary slice. This is your distance. Now, what is that distance at? What's that distance? Remember, you take the what? Larger, subtract the smaller. So that distance should obviously be 5 subtract the arbitrary y value where this slice is located. So there is your distance there, 5 minus 1. So we know the force, and now we know the distance. So let's go back to here. So our distance then, our distance will be 5 minus y. And that's looking at your model right here. Okay, that puts that together. So now we have that. We have our force and distance. Now finally we can finish this off, and we're going to do this quickly so we can take a break here. And so finally, okay, your work is equal to, okay, we're going to integrate. Now, here's the thing to pay attention to. your fluid only exists on this y-axis in the tank. And the tank only exists from y equals 0 all the way up to 3. So you're going to sum up these partitions, your slices, from y equals 0 all the way up to 3. That's the fluid level. So we integrate from 0 to 3. What's our force? That was right here, right? So your force is 9,800 times 8 times y, and then delta y, that becomes my dy. So what I've drawn here, up to here, that's your force. But now we got to multiply by distance, which is 5 minus y. Okay. So there it is. That's force times distance, and you're summing them up from 0 to 3 to get that, because that's where your fluid in the tank is. So if you work this out, I'll let you do this on your own, but 78,400 is 9,800 times 8. And then you have the integral from 0 to 3 of 5y minus y squared dy. And if you work that out and you get a final answer, here's what you get. I'm not going to show it. 1,058,400 joules. 400 joules. And that right there is the final answer. Okay. So there you go. The tank problems, there's one of those. So, okay, so we need to relax now. So let's take a break here. And let me stop this here.